So, welcome to week 5. As I told you guys earlier, we will do that, which is if you submit on time with the current deadline, you get extra credit. In a similar fashion as system skill, then we'll extend by 3 days. One last thing, we'll make sure we cannot do this for the last project. All right, there's no way I can do that. OA will yell at me because I will submit the grade late. I cannot do that for the last project. So clear? Any question about that? Because it seems like everyone would like at least some deadline, some extension on the deadline. You don't? You okay? You're done? All right. Then you should enjoy extra credit. Don't make the whole class murder you because you said, hey, just have no extension. All right. Yeah, I shouldn't make any more jokes than that because otherwise they'll start ganging up on you. Not good. That's cool actually. So today we'll talk about low-level IO, which is kind of like a topic we have to go into before we dive deeper into how, like, say, how can we have two computers talking to each other, all right, and how to have functioning internet. Before we begin, we have to wrap up the topic that I say, hey, I will not talk about this because it will not be on your exam. It's a little bit the extension to like the protection and the security topic that we went over, all right? So these are things that are handy to know. For example, recall this. This might be on exam. The principle of protection, follow that. Basically, I assign the privilege level to a program, a user, or a system, and it should be just enough that they have, like if they have to do X, Y, and Z, the permission is just allowed just enough so that they can do X, Y, and Z, and that's it. Because if you allow them to do more, it can be damaging to the system overall, right? How many people seen, like, for example, you go to Android app store or even like Apple app store, right? And you look at the app and like, why do you have to grant this weird permission for this simple application? Anyone seen applications that are like that? Like Apple, for example, I think there's a section that say, hey, these are the data that's linked to you. And these are the data that the application is using that's not linked to you, right? Some apps that are super simple should not be able to, like, should not use it, should not use these permissions, right? So again, the principle of the least privilege, when you develop any, again, also apply to like mobile, when you develop a piece of software, limit what you have to access as well, because otherwise your app will look super sketchy, right? That's more, I would call it system of protection, basically the protection mechanism that implemented, which is kind of like everywhere that we use in everywhere, like all the in many of the computers we are using. For example, in Mac OS 10.11, right? They introduced the system integrity protection, which restricts the access to the system file and resource even by the root. This is important. Even the root cannot access certain things, right? Then you are allowed to extend a file attribute. Basically, when you have a file, you can change the attribute to change the restriction. You can also disable things like debugging, because sometimes people use debugging mode to attack things. And only code sign kernel extension are allow and configure. I think the key thing is also not just allow, but also configure. Okay. This is what we call system integrity protection. Another technique that also is introduced is system call filtering. Since system call filtering is more of the filtering technique that behave like a firewall. Anyone heard of a firewall in computer? What is it for? yeah, protect my environment, right, from the outside attack, right? And the way it protects is like a firewall, which is like a wall basically. And then you burn the wall to make it harder to get in. Basically, you block certain access based on certain patterns that you can detect, right? These are the way this behaves is kind of like a firewall, but for system call. So it filters system call and can also allow like you to inspect the system call arguments. Linux, for example, has this Berkeley packet filtering to implement the feature similar to system call filtering, right? Unlike the system integrity protection, which are like, okay, this file cannot be accessed even by root, like only certain people can configure them. This is more like, okay, I cannot run this system call based on my definition. Now in Android, what's the unique thing about Android? You can have multiple applications, right, running on your phone, and each app should be isolated. Basically, one of the unique features of phone applications is when you open an app, they should behave like a total isolation from other apps, right? So it kind of makes sense in this case that I would then assign the user ID in a per application basis rather than per system, which is like the system has all these users. Now, each application has its own user ID assigned in a more like this user ID and application pair, right? And when you install a daemon, when you install an application, you install the daemon that assigns the distinct user ID and group ID. And this is the unique part about Android, right? In Linux or even in Mac OS, if you install a program, it's going to be installed in a certain directory that you specify. It's going to be somewhere in your computer, right? And when you browse through, you can access those files. So in this case for the phone, one thing that I can do is I have this protection where if I install an app, it will be all the data associated with that app will be in this directory, which simplifies things like restriction, right? If I'm running app A, I should not be able to access the other app's directory. Now that I have the user ID in a per application basis, it's much cleaner because I have each directory for each application. Think of it as now it's become your home directory, right? And who can access your home directory is tied to the user ID. Application on device has then the same level of protection provided by the system to other users. Basically, the application would then kind of looks the same and has the same protection against the other application. Why is this nice? Because somehow you run like multiple apps together, right, on your phone, and you want to make sure that the information doesn't leak from one app to the other unless they intentionally want to do that, right? Unless they intentionally want to do that. For example, how many people kind of realize that when you have to like say, for example, you have a picture, you want to then transfer the picture into the email, right? You basically have to kind of share that picture into the mail app before that becomes the attachment, right? So that becomes like the kind of the protocol to communicate with each application that is dictated by the system. Huh? Then the permission becomes like the user actually has to hit the button to share, right? To grant the access. I'm gonna share this to the central method to another app. Now they would have another basic access to this copy of the file from this original app, which I can use later. Right? Why is this the case? Well, first of all, it's a protection done quickly, right? And it's simple. If you think about it in an abstract high level sense, this is quite simple, right? So in Android, we have this thing called trust zone, right? So the application that needs, say, for example, the cryptographic service, I would then use the framework. When I said vendor supply, what do they mean? Anyone want to make a guess? What does vendor supply mean? What is a phone vendor? Can someone give me some names of like different Android phone vendors? Samsung, right? Google, for example, they have their own phone as well, right? Basically, all the companies that produce the phone. Why? Why the framework is based on the vendor supply abstraction layer? Are all the phones from different companies, do they look the same? That's the That's how I would actually put it as one of the major trade-offs of Android system design. I built Android, I have to build it for all the vendors, right? Unlike Apple, which has the kind of the simplicity of this thing is used on only on my hardware, and that's all. In this case, the vendor can add whatever hardware they want to add. So in this case, the way they do it is like, okay, vendor would supply the hardware abstraction layer that would communicate with the trust zone daemon that would think of daemon as like some like a process that the system would invoke and maintain, right? So that's the key store and the gatekeeper, and then the privilege mode again also supplied by the vendor will issue to the driver. What do the driver do? As the name suggests, whenever you see the word driver, it drives the hardware. It's like another piece of software that runs your hardware, right? So now I can send a request to the trust zone that driver. So this is like application layer you can call. Then it calls the driver code, which is now in the kernel. And then when you call it through trust zone, now this thing can be trust. The assumption is this thing can be trust. Why is this useful to have this kind of trust zone kind of thing? Because these API allow each vendor to just basically operate the way they want it to. It's not dictated by Android. It's dictated by how the vendor implements the trust, like the use, like the privilege mode. The concept is done from Android point of view. Which is I have the trust zone. Here's the concept. You go implement your own framework so that it works with this concept. Now I have the trust zone concept. I have the framework from the vendor. If you have to develop app for Samsung and for another different Android phone, works the same way because high level it works the same way. High level I just use trust zone. All right. Oops, sorry, I think that's a copy of the same slide. Now, the modification to the kernel would allow like certain operation to just members in Android, just member of particular group. For example, I can establish a network socket, which we'll learn actually on Thursday. What do they mean? But think about it as a way for two computers to communicate. And certain user ID are also isolated, which means that I can only call requests to just the minimal set of services. When I call the service, most of the time I can do this to what I would call RPC, which is remote procedure call. It's procedure call, basically. Think of it as function call. I can call from one location. I send the request, call this function for me, and the target will do that for you, reply. For how do we implement the RPC with 4 more weeks, we'll cover that. All right. We'll cover that. I'll try to kind of briefly go over gRPC, which is Google RPC per se, but they don't call it Google RPC from Google. Like Google don't call it Google RPC, but you kind of know it's implemented there. It's really low overhead and its performance pretty good. All right. So that's the Android. ARM CPU architecture, the way it works, this is a little bit more about the, if you think about it, it's more of the the mix between mobile, because ARM is used in mobile, right? So it would have some of the features that like Android Trust Zone would like to have. For example, I have this trust application from the user, right? Now, what's the if you look at EL1, well, you have the user, you have the kernel, right? Don't worry, you don't have to worry about EL2 and 3 for now. Those are more like for the virtualization. If you want to actually enable things like virtual memory, virtual machine, my bad, not virtual memory. How would you do that? But look at the kernel. Look at the kernel, right? That's a kernel for application group 0. That's a kernel for application group 1. And that's also the trusted secure kernel that's totally isolated. Why is this nice? I can't reach into the secure kernel unless I actually, like the function call I'm run is trusted by the OS. The way you would establish the trust depends on how you implement it, but the concept is I have to trust them that I can use the secure kernel to call them. All right, so that's kind of a quick recap on the Android and ARM side on the protection. Now, security, right? So we talk about this thing like threat. What's a threat? What's the attack? Threat is like things that are potential, right? It doesn't mean that people are attacking it yet, but it's a possible threat that people can attack this part, right? The attack is the one that actually now attempt to breach security, and we talk about different type of attack from like a Trojan to a worm to like a spyware and things like that last week. Now, one thing I kind of want to briefly go over is, well, you also can use the hardware to help protecting you. What do I mean by that? From your point of view, right? Most security implementation are done in software, right? It's protected by the OS. It's protected by some program that protect the OS. What if I cannot trust the OS? So if your assumption is my system will protect me, the argument is, what if I cannot trust the OS? Right? So one potential idea, how many people realize that your CPU also has the like secure method to do things? For example, if you watch the like Apple product launch, right, the iPhone, there was a time when they actually talk a lot about security chips that they have. Why is that nice to have? It's another layer of protection, right? You have the hardware to keep protecting your data as well, because sometimes you cannot trust the OS. Sometimes you cannot trust the OS. So now, from the hardware side of things, you also have the special hardware designed to protect your data. So, for example, in the Apple world, you have this concept of secure enclave, which is I can kind of explain it this way. It's going to be a region of memory that say no one can touch this. Why is that nice? Usually, when you think about the kernel, I can touch everywhere in the memory, right? Because the kernel is the basis of, hey, I want to touch the memory and I want to manage them. The point of the kernel is to manage the hardware. Now, the secure enclave is like, okay, I'll make sure that if you want to access these data done through my hardware, because I don't trust anyone, including the OS. If the OS want to use these, use the hardware assembly calls, if you think about it, if you will, right? It's like these instructions that give another layer of protection. So we have Intel XGS or AMD SCV works kind of the same way. It protects like against the case, right? The case where the OS is breached, or the OS had bugs that someone can attack. And now, okay, now I still need to rely on the hardware. All right. Aside from that, you can also attack the hardware. most of the time you think about attack, right? How many people here know that we actually, system skill server, right? It was attacked last semester. It's still down right now. That's why you cannot access it. Basically, we take it down because we kind of need to figure out how are we supposed to manage the server with the manpower that we have and not die because we have to do multiple things. Anyway, so basically we ended up taking it down because we kind of don't want to always use the IT department as well, because the system skill server, we want to open more ports and make sure you can do crazy things on it to some extent, right? But not attacking it. It was attacked by a software attack. Basically, someone got in, elevated themselves into the kernel privilege by some bugs in the system, right? And then now when you take over the machine, it's done. Basically, now that skill server start attacking everyone else, but it's from the software. How many people think about hardware attacks? What are the potential things they can do into hardware? Yes. USB, so the thing is, USB is actually a software attack. You plug in the piece of code attached to USB, right? The OS reads the USB and then something happens. It's software level attack. When I mention hardware attack, basically it's things like sometimes we call this side channel attack. Anyone remember caching? Caching from Cisco, right? So what's the benefit of a cache? It's fast. My data access, right? So let's say I have the data access. Used to be this much to go to the memory, but only this much to go to the cache. So if I have the address, right, it will take some time to get my data. If I have to go to the memory, it takes T1. If I go to the cache, I take T2. And then T1 is much more than T2. Clear? This is one thing I can do. So this is the victim. It's running. This is the attacker. The first thing I do, the attacker flush the cache. When I said flush the cache, it means that I get rid of everything in my cache. There's like assembly code that you can do that. There's an assembly code that you can type one line, everything in the cache is gone. All right. Now, let's say the attacker wants to figure out whether the victim access address 1 or not. I would just want to see, hey, does the victim access that address? What do? I flush and then I load address 1. Now, what is in the cache? Address 1 is going to be in the cache. From the attacker constructed the attack by first get rid of everything in the cache, then put only one thing in the cache, address 1. If the victim doesn't have to access address 1, what will I see? Every data access takes T1. If the victim has to access address 1, there will be one instance of I measure the access time, T1, 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 oh, T2, T1 again. Now I know the victim has to access address 1. And I keep doing it. So these are like what we call timing attack. It's attacked by looking at the time the victim has to access the data. And if I keep doing this, I can have the range of address to say, hey, okay, these are where the data is, right? From the assumption, should I be able to tell the address of the other process that are accessing? No, because those are either data in the cache not exposed to the programmer, or the address from the application, the other application that are running, also not supposed to be exposed, right? But you can use the timing attack to do this. When was Spectre and Mel? I think it's 2017, I'm not sure. It's sometime along that line. Another set of attack comes in called Spectre and Meltdown. This make quite a bit of an impact because what they do is they use this timing attack to figure out the address and then attack a few more things in the CPU. We can talk about this when we talk in module number 3, because then you have to learn a little bit more about how the CPU works. But the way it's done is, now that I know the address, I can write the attacker such that I can then peek into that value. I can systematically read your data. This impacts, one of the attacks impacts like Intel CPU, the other one impacts kind of basically all CPU. Yes.
So for the spot,
Yes.
but the thing is that how they get there after
the thing is, I don't know. Basically, I don't know what is the address the victim is trying to access, but I want to figure it out because I mean, basically, I want to know the location of where should I attack in the memory, right? The way I can do this, if I let the victim run without flushing the cache, I mean, some access will be fast, some access will be slow. I construct the attack such that only access to that address is going to be fast. And the way I can do this, I load that address into the cache. That's the only data in the cache, which means that every other thing is going to be slow, right? Then I check how long, then I can just basically measure how long does it take for the CPU to access the cache. I keep doing that. Because sometimes I'll be running, sometimes my victim is running, but I keep measuring the cache access time of the CPU. If I see slow, like all slow access time, I would assume victim doesn't load that address. But if I see slow, oh, really quick, and then slow again, it means that the victim actually has to access the data. And I can keep doing this until I know these are the range of addresses I want to attack. Again, now I know the address. Vector and Meltdown kind of like use another set of attacks to, now I know the address, I can peek into the data, and then I would disable exception handler by the OS. Because usually when that happens, right, there'll be some like sec-fault-like kind of thing, which would crash the program. In the paper, say, hey, you can do something like atomic, which means that if the exception is done during the atomic operation, it's either basically no exception is raised because that whole operation should never happen. It run, oh, something bad, so we try. But it doesn't crash the program, so I'm good, right? One more thing, I guess once we learn about DRAM, I'll talk about this more detail. This is an attack that the lab that I graduated from, we discovered this in 2016, 17, like around that timeline. We basically, one of my friends testing DRAM from like multiple vendors like Samsung, Hynix, Micron. These are the 3 major DRAM vendors. I mean, if you haven't realized, one of the biggest product from Samsung is not the phone. It's actually DRAM. That's what they do. And they're doing that really well. Anyway, so we're testing DRAM from multiple companies. And then the goal of the experiment, we want to study about like, okay, what's the error rate that we're gonna see from a normal operations. And then my friend saw weird things that are happening because we're expecting, right, the error would be dependent on where we are modifying the data. But then let's say we are modifying the data here. We start to see error popping up somewhere close by, which is really odd because that's not supposed to happen. Physics should not let that happen. It's like we should not be running on magic. We are not doing anything to that data. Why do this? Like, why is the data wrong, right? So we discover a little bit more, and we can basically I think 6 line. He basically came up with a 6-line assembly code that can systematically do that all the time. Now, all the major manufacturers have been patching for this attack as well, right? But my key takeaway is hardware attack also happen. Don't trust one single entity then that they'll be clean. You might want to use multiple entity to give you security, right? As long as the user didn't realize that these things happening. How many people have antivirus software installed? Why? The paper that talked about attack, I said earlier, the flush the cache, load one address, and keep going. That's the paper. A quick PR, if you basically, my research group is planning to do a reading group on that paper. Next week, Wednesday, if you're curious, let me know. Basically, it's 10 o'clock in the morning. My student want to check it out. Basically, the whole thing is like, we'll talk a little bit, maybe 10 to 15 minutes about the paper, and then the rest of the discussion about what other things we can do, what are the hardware implementation we can do to kind of like prevent against this attack, what are the new attacks based on these kind of things. If you're interested, let me know. Anyway, so that's it for the OS side. Yay, module 1 is done. Now, as I said earlier, we have to keep going. Quick recap on the system, right? If I ask you now the question, what is a system? Basically, it's a bunch of components, right, that I have that are connected, and then I expect that if I look at this system, it behaves the way I would expect them to be. It should run the way it's supposed to be. A well-designed system, when you use it, you should never notice that they're running. Why is that the case? If you use some version of Windows, I won't say some what version, you might have noticed maybe I should not upgrade. I should keep it that version because they are faster, right? So the one of the major goal of a good system is the user should never realize that this thing are running. Because whenever they realize there's a system running, most of the time it's either, hey, this is too slow, some bugs happen, I cannot access the system, something goes wrong. It's almost always a bad thing. What makes it difficult? You probably know by now with the project 1, complexity, limits what we can build, debugging. You probably have a joy of your life right now, debugging your project 1. So I won't go more than that. Mitigation is weird. You cannot simply do printf and expect that you can debug the whole thing. You might end up going back to, okay, these are the design principles that it's supposed to happen this way, and you keep staring at your code, hopefully to identify things that doesn't go according to that. And you're nodding your head. Many of you are facing that right now with like the latter half of project 1. Now, quick note on module 2, right, is about computer network. There will be a lot of material, used to be one big class, like one semester length class that we cram into a mix of 3 topics. We cut a bunch of components out to boil it down to the concept that you should know and you must know as a CS computer science students. If you want to learn more, there are more advanced class for this. For now, we might have to go a little bit fast, all right? There'll be pre-lecture available. For this one lecture, it's post-lecture because we don't have time to go through that. The post-lecture for lecture 8 will be on the video, we'll say lecture 9. Because back in the day, this is supposed to be lecture 9. I do not count the midterm, the exam as one lecture. So the lecture number will shift a little bit. These are from Ajahn Kanat, so thanks to him, I kind of watch it like this is perfect, so I'll keep it that way. You can go watch the pre-lecture. Each class will also have its activity, so an activity comes back. Yeah, not sure if that's a yeah, but yeah, it's a practice. Previous semester recording and slide from Ajahn Kanat is available on the syllabus page. So you check out the syllabus page, it's all there. And also there's a really, really nice online book that we use as a reference. You can go access it and everything that's free. All right. It's actually MIT Publishing, and then the detail in that is really, really, really detailed. If you want to dig deeper beyond what we cover, it's all in there. All right. So here's our system so far, right? We have the OS, and we have a bunch of process running. Process A, B, C, and D. They're running. Hopefully everything works. Now, my question is, how can I enforce modularity? So what do I mean, first of all, what do I mean by modularity? All right, can someone look it up quickly and tell me what Wikipedia or Google tells you guys?
Or property that describes how invisible the components of logical.
Yeah. Things like if I take a component out, how easy it is for me to have the running system again by plugging in another module, right? So if I have, say, in this case, like monolithic OS with the system running a bunch of processes, right? And I want some form of method to connect this system up. How do I design it such that I can connect whatever machine I want to connect to? Think about it this way. x86 machine connected to the internet. Mac OS connected to the internet. iPhone running a totally different chip connected to the internet. Then you have a bunch of Android. And then there's even more like IoT device, right? How do I let that happen? How do I enable that? So the first thing we have to talk about is what we call the client-server model, right? And you might, when you see this word, you might have recognized, right, that the server is like a machine in the middle that kind of facilitates communication and run things. The client is like your machine that you're working on, right? So in the local version, let's say this is basically on your own machine, right? You can actually run, right, a program that the first send a sorry about animation bug. The request, the arrow from left to right supposed to happen first. That should not be the arrow from the right to left yet. Basically, the client say, hey, I want to run factor. I want to run factor. And let's say factor is defined, right? Defined in another object, right? And I send a request to that object and say, hey, run this method. I want to run this method with this input. So the server say, okay, I will use n as an input. I will run this code here and returns back the number. Then I reply. You can think of it this way. Basically, function call, right, works the same way. I call a function, something happens, I get the return value, right? But this is locally on one single machine. Now, modern day computer is a little bit more complicated than just one machine, right? Imagine, for example, I go to a network and Google spider cat meme. Basically, what happened is from my machine, right? I will call or data, basically a bunch of data coming back to your machine. Now, that's this bunch of network, right? And then if you look at the internet, how many servers that you can see? I mean, think about it, it's still the same model. Like I have a client, I have a server. I can talk to the server and get a reply back from the server and run it on my client, right? But how many connections are there right now? Client side, server side, it divides a bunch of program running on the client and a bunch of server. All right, decide questions, right? Should we take a quick break and stop at this? Hopefully now motivate, like, okay, how do we even design this thing? All right. And we will design this one step at a time. Okay. We will design this one step at a time away from your client to connect to the server and get something done. Now let's take a 10 minutes break. We will be back at 11 o'clock and we will resume the lecture. All right. All right, so let's resume the class. How do we design this? All right, here's the design elements. First of all, if you want to program with this client server model, right? If I want to program, basically, because everything you do is coding. Basically, you are the developer. You write codes, right? How do I take that into account and build the program for that assumption that you have the internet and you can connect to the internet and you can send requests over to the internet? What should be the piece and how do they work? How do they work? What are they? So this is the fourth bullet point is something that I would like to stress when you get more and more senior, right? Go into 30, 40. This is one of the things that will keep coming up. What are the trouble spots or concern that can break your system, right? I mean, in your life, many of you use the banking apps on the day that Hoi off, which is like it will be super slow. I mean, ever wonder why can't we build the system that would handle that? If you know the traffic will go up, right? So a more senior people might be able to kind of figure out, okay, maybe we want to build a system in a certain way to handle this thing, right? So here's the design goal. Basically, first, for the internet, you need to understand what happens when we turn on our computer and make the request over the internet. If you go to Google, what actually happened? So that's the first thing you have to understand, right? And then the second thing you have to understand, you will get a response eventually. Somehow it doesn't happen. If the server goes down, what are you gonna get? Yeah, something like 404 things that don't exist. I ping the server, it's like connection reset. Have you seen that as well? If something wrong on the server side, it resets your connection, right? And then it should be enough to know when you are working with a commercial grade server, right? You need to be informed of what the system looks like. Basically, if you have to work with the internet, you have to be informed how are you gonna talk to the server. So the two design goals, first of all, you need to know what happened. Second of all, you need to know how to talk to the server. And third, you need to know eventually the server will reply back to you. Is that enough? First of all, you know what happened. Second of all, you know how to communicate to the server. Third of all, you know that eventually the server will communicate back. Is that enough? Somewhat, right? Assuming that you don't dive into the infrastructure and think, okay, how do we connect everything up? This model is sufficient, right? Keep this. Now let's go forward. The thing is, right now, right, the client server model gives you a really nice isolation. You have someone calling something, requesting procedure. I want to run X, I want to run Y. And I have this isolation between the client and the server, right? Here is the detail. Basically, in most cases, in system, the devil is in the detail. You realize that in project one already, everything sounds straightforward until you implement it and run. Then everything breaks. So let's actually now think about, okay, um, let's sneak out of this isolation and see how do we implement certain things. Start with the low-level IO. So if you watch the post lecture, basically we will talk about the low-level IO, and here's the goal. Everyone use printf, right? How do we have that done? Well, if you think about it, right? If I want to design something that would allow me to print some character on a monitor, right, it means that there has to be some hardware that reads certain letters, certain data, and be able to work with the IO, which is the monitor, and show the correct symbol on my monitor, right? So here's what Unix low-level IO give you. The goal is I want an interface that map, what is seen as a file, because I mean everything on your computer, you can think of it as everything as a file, right? So what is seen as a file to the underlying device slash storage slash thing. The reason why I said thing is because that can be many other things like network interface card. It can be like reading from your IoT device that comes as an input, right? It can be your disk, which is your storage and other device like a printer, right? That's why we classify this as like IO. And here's what you now that you think about everything is a file, right? You treat the IO, your hardware that reads this stream of data. Because if you think about it, it just you send the data out and they'll handle that, or they send the data into your program, right? It means first of all, if I treat that as a file, I should be able to open and close them. All right, I should be able to open and close them. I should be able to read and write to them. All right, are we done? Pretty much done. That's optional thing. For example, I might want to change where I am reading from one place to another because I can, what if I can jump from here to here quickly rather than having to read everything here, right? So that's the optional part. I would like to be able to change the current position of where I'm reading right now. If you think about everything you're reading as a file, it means that let's say you're reading the first line. Can I jump to like the fourth line or the fifth line from the first line, right? Uh, and then the rest are like, okay, do I attach things like metadata, which is additional data that's not a part of your file, but it talks about the file, or like what's the properties of the file? Is it like the image file being edited on this day, right? You notice when you use a file, for example, you have like modified on, right? Which you can sort. You can sort your directory based on the last time you modified the file, right? Those are metadata because the time you modify the file is not a part of your data. It's a part of the information that are useful for the user. So we call this metadata. The sharing statistics, right? Are we sharing this particular IO? And do we support redirection? Recap, what's redirection? Like the greater than, less than sign, remember that? Wait, think about it this way. We call this redirection because we from one IO type, we can redirect to another, right? And one common thing that you use so far is what we call standard IO. The standard IO is inside the C standard library or libc.so that contain the collection of these high-level basic IO functions that you use so far. Any question about how to use those things? Okay, cool. You should not. All right. Now, every process that you create inside Linux, right? You might have realized that you have the standard input. What is standard input? What is standard input? Oh, the interface that you type in, like things from your keyboard, you type and hit enter, those will go through as a standard input. Then you have the standard output. Usually when you run a program and call printf, right, those are standard output. And then there's a standard error, which only captures the error part. For example, you have a like you run GCC and it spits out the error. You can actually just stream out the error complaints and not the rest. Now, from the user point of view, right, when you run the C program, you have stdin, stdout, standard output, and stderr. So that would kind of directly map from the three Unix version of the process standard IO. And inside Unix, inside your shell, right, the stdin is called stdin file no 0. File no is file number. This allows you to basically simplify this whole thing. Again, we treat IO as a file. If I can treat IO as a file, I basically say that, okay, file with the ID 0, that's your standard input. File with ID 1, that's your standard output. And file with ID 2 is going to be standard error. Now, if I want to handle those things, I just read and write to the file. But now the file ID is going to be 0, 1, or 2. Right? Think of it as you have fprintf and fscanf, right? Directly on this standard input output. Now, the standard IO is implemented on top of the low-level Unix IO. Right? So we have a C application program running. You have standard IO function, your old friend like printf, scanf, right? Printf, scanf. All right, these are what you use so far. These are what you've seen so far, right? Those are the functions you can call easily from stdio.h, right? I can do fopen, fscanf, fgetS, right? Now, there's an underlying implementation. Basically, it's like, start to ask the question, all right, how do I implement fscanf? How do I implement fprintf, right? Because, I mean, standard input is 0, standard output is 1. So you can think of printf as fprintf, where the file descriptor is what? 1, right? Fprintf 1, and then whatever you want to print, that will print to standard output, right? Then scanf is fscanf, where the input for the file descriptor is 0. That's a standard input. All right, now you have the Unix IO function or system call, which is just open, again, what you have to do, open and close the file, right? Read and write the file, and then the lseek, which is jump from one place to another, and then the stat, like look at the statistics. All right, so what are the design philosophy and which one to use in a program? Quick question. For the most part, will you ever use the bottom part, your Unix IO function? Not really, right? Why? How many people want your program, when you write a program, you want your convenience? It's actually that. But here's the question. Then if I say that I want to make sure my life is as convenient as possible, why do I need the last 6 function call? Here's the thing, right? If I want to support interoperability, because what I assume already is every single IO is treated as a file, right? And I can open, I can read, I can write, and I can close them. open, read, write, close, right? It means that if I just do this for function, I treat every single IO like network sockets, regular file, block device, your terminal, like standard in, standard out, everything is just a file. Then I am good with just these Unix IO, right? I can convert scanf to Unix IO. And it should work with network socket. It also should work with, say, regular file. I can, again, I don't have to do F open for one of them and like F write on another, right? I can just say open, read, write, close, open, read, write, close, open, read, write, close. So it kind of allow you to, at the lowest level, everyone use the same thing. At the lowest level, everyone use the same thing. But sometimes, for example, in the block device, you might not have the F printf. It still have this Unix IO that you can use. It gives you the tools that in the ultimate case, if you don't have the higher level function call, you can use this simple function of open, read, write, and close, and else. All right. Now, IO is slow, right? Everyone kind of noticed that. If you read something from the disk, it's going to be much slower than, say, your DRAM. One other common trick that we use to implement this IO is what we call buffering. What is a buffer? It's like empty slots, right? So here's what happens. When you have to do read-write system call to the file, these are always expensive. In the range of like microsecond or millisecond in some cases, if your file is huge, right, that can be milliseconds. And when you use a file, right, let's say you do F scanf, how many letters are you reading? Like maybe less than 80 letters, right? That's 80 bytes, right? But your IO is operating in a much bigger block. It can be like 16 kilobytes block, right? So you say, hey, I want to read that part. It performs some operation that takes a long time. And now you have the data that are like 16 kilobytes flooding back to you. And you as a programmer say, hey, I want that 80 bytes from it. That's it. The rest, let's throw it away. Is that efficient? What's the better idea? All right, let's say you open a file. What's the likelihood that you are reading basically the next line? It's really, really highly likely, right? So this is like a block of data, right? You're reading this part. It's really likely you're reading the next part in like 5 more lines in your program, right? So the better idea is, okay, I got this for 16 kilobytes or 4 kilobytes chunk of data. I put that in a buffer inside DRAM, for example, so that the next time I need to read the next part of my file is not in this. I don't have to issue another IO request to get that small chunk. We call this buffering. So you maintain a buffer which can be implemented in the software. Basically, you then write a piece of software, do the fread, open a file, read a big block of data, and maintain that data in some buffer in the program. Not in the application level program, it can be in the kernel level, for example, right? Maintain this buffer. When you grab a block, you put them together in this block and say, hey, unread, and that's fine, right? Then I read one byte after another, so I keep consuming them until I'm done. So this is like, say, 4 kilobytes. And I keep reading the file, right? This can take like maybe 10 different for loops to reach the end. When I'm done, then I read the next block. Because I can kick this out, right? I know I'm done. I read the next block. I put it in the buffer and do the same thing again. So standard IO function use buffer IO. When you are done, in the standard IO, the buffer IO flush. So basically these are your buffer, right? When you want to say do the printf, you can't keep buffering. You actually have to flush them out to the actual location, right? So whenever it sees these things like /n, like new line, f flush or exit or return to the main function, this buffer is flushed out to the target. Why do we do it at the time you see /n or f flush? Because that's where the target needs something to show to the user, right? So let's say you do this. I do printf HELLO, and then the last line printf /n. I can then add f flush to the standard output as well, right? So that's like my stupid hello with new line. What would happen inside the buffer is it would basically, even though we do printf, right? These are treated as a file, and when it's treated as a file, these are IO. And IO again takes a long time. So what do you do? Buffering. I put H in, E in, I put L in, O in, and then I get the new line. If I do the stress command to run this program called hello, like basically, let's say the program is called exactly that. You will see that after this, like now that it's the right, right? Basically, the Unix implementation. See, this is Unix IO. So the underlying implementation of your printf, it actually uses your Unix IO write command to write to the buffer, and it writes the whole thing hello /n, right? 6 slot file descriptor. What is file descriptor here? Standard in out or what? What's number 1? Output, because we're printing, right? Printing output. If I do scanf, that becomes 0. Then I put these letters into the buffer. What's the size? 6 bytes. All right, then I'll see flush, which means that it's time to actually pour out this letter hello with the new line into the standard output, which is your terminal. All right. Which one is easier? Method 1 or method 2 here? From the programming point of view, like from the programmer point of view, which one is easier to use? The function called write with the file descriptor and the size and the buffer, or printf, right? So one other thing is the trade-off, right? Unix IO give you the lowest overhead. It's like exactly what you have to do and not more. Nothing more than this. This is like exactly what you have to do. That's it. This is fast. It provides a function for accessing the file metadata, because if it's a metadata, you might not be able to see that from like scanf, right? But it's somewhere in the buffer, so you can read them. Then it's also async signal save. It can be used safely in the signal handler. Again, signal can happen at any point in time. Let's say I do Control C, right? And the programmer predicts when will the user hit Control C. Really, right? Can be at any random time. What are the downsides? Well, first of all, it's tricky and prone to get everything correct. So if you have the better option, use the better option, right? Some buffering is required. You will have to implement buffering on your own. And both of these are addressed by C standard IO, printf, scanf. These are much more efficient in terms of implementation. It's good. It's not more efficient, it's not faster, but it's fast enough. Standard IO like printf and scanf, the benefit is it already have the built-in buffering. When you do printf, the whole thing implement buffering for you. You don't have to do that on your own. And you have, if you do like short reading, like scanf, 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 because their buffer is done by scanf implementation. Downside is you can't easily access file metadata. If you're dealing with signal handler, that might not be safe. And it doesn't work on network sockets, which we'll learn on Thursday. To choose, there's a general rule. Use the highest level, not the lowest. Use the highest level for you. That works. In C, avoid going read and write. Use printf, scanf, printf, good for you. All right. But you have to understand the function that you use, because sometimes it's not there. Like if you like do say socket programming, you cannot really like use scanf. When you use the standard IO, it's like when you use like working with disk, working with the terminal, for example, the raw Unix IO is better if you have to do the signal handler or network sockets, or if you absolutely need to re-implement printf for performance, which doesn't happen a lot, to be honest. All right, so today there's a demo that because everyone also have a computer, that the code is actually on Ajahn Kanat GitHub. You can do git clone to get the C code from there. You can try it on your own. You can actually just look at the code where I'm gonna run. Basically, what we will do is, first we will copy the file from source to destination. Basically, we will build a program that do CP. The second one is it's going to be a program that do the command T. The command T is take the standard input and print it out. It print out the standard input content, whatever you type in, into the standard output and a file. Then you can do LS, directory listing, right? Because someone has to implement that, so let's do it. Okay. Quick thing, if you look at the starter, like the demo, you will see that it used this direct.h. It's the directory structure that you can use. In the directory structure, it contains two things: the serial number of a file, and then the string for the file name. This is a file name of this directory. Basically, it's a struct that contains directory management that you can call. All right. So I'll give you guys some time to download the code here. I'll pause the recording. All right. So for copy, right, it takes two input, source and destination. And the idea is simple. I read everything from the source and write it back to the destination. So here's what I do. I create two file descriptor because I need to make sure I know where the file is, right? So I would do in FD, which is the input, and then out FD, which is output, and I open both of them. The open text, first of all, is the location of the the file you're reading. So in this case, the source. And then followed by the option. In here is read only. Why do we open it as read only? Because when we copy, we are not modifying the source, right? We're not modifying the source. And then here for the destination, I can copy into a new file, a new location. I can copy into an existing file, right? Because I mean, I can copy and replace all files. So I need multiple options here: create, write only, and truncate, so that I can overwrite if the file exists already, right? Then it allows me to overwrite the file with the new file. Then numRead is basically the number of bytes that we're reading. size T is the size usually in like n bytes, 1 byte, 2 bytes, 3 bytes. F size T is signed version of that. It has a positive and negative number. So while we are reading this, right? The reason why we use F size T is if the source doesn't have any more data, right? I'll get something like 0 or negative number. But if I'm reading any bytes, I write it to the output. It's as simple as I read in FD, right? In FD, and then the buffer size right now is 1024 bytes. So I do like block of 1024 bytes at a time. I read them to where? To my own character buffer. Now I read 124 bytes at a time. I go to this, say, okay, give me 1024 bytes of data from the file, from the beginning to the end. 1024 bytes at a time. I read them and write it back to the output file, and then I close the two file descriptor. Any question? Again, open, read, like read, write. I'm done. Close. Now, here's the T command. Again, the T command is also simple. I read something I'm typing in. And it basically kind of echo that to the output, the terminal, and then write to the file, right? So the T command, first of all, you have the file descriptor. And it can be like more than one output location, depending on what you want to put in. So the command is T followed by the file, like file name. Once you hit enter, you type in whatever. Those things you're typing in is copy over. So this is kind of almost similar to a copy, but now your source is not the source file. The source is the standard input, right? The source is the standard input. And the destination is all the file you put in. So here, the first thing we do is open the output file. So let's say you do like output to 5 different files. You open them all into your array. Then you, again, have the buffer, right? Then you read not from a file, but from the standard input. So it's stdin file node. These are like static number that the computer know, okay, these are from your keyboard input through the terminal. This is through the terminal. Then write to every file. Then afterward you close them. Question? So this is almost like a copy, but the source is your standard input. The destination is actually many files that you list out. Now, the last one is ls, right? So the ls command, when you type in ls, basically, first thing you have to know where you are. The way we do this is we can call the function called opendir. OpenDIR allows you to open a directory, and let's assume right now we want to open the current directory, so I just do the dot. Yeah, dot is the current working directory, right? Then we start to create the entry for the directory, and we use the command read dir to read this path, which is my current directory. That path will be read and it returns this directory structure, which I show here, right? It has the serial number and the file name, the list of file name in the directory. So now that we have the file name, right? Then I can look at the attributes. So I can do the type, this like directory, for example, or a regular file, right? Or a block of data. Then you print them out. Now notice how in this case, I can just do print out. The reason why I do printf is because I just want to print the standard output. I already have my file names in the struct, so I just loop in and print them out. Then afterward, I do close dir with the path, basically to wrap things up. And that's it for the demo. So please, the last 10 minutes, please go check out the in-class activities. It should be on Canvas. Here. All right, so today we will do a lot more malloc memory allocation, basically extension from last week. So a quick recap, right? We talk about memory addresses where when you want to use any data, they're going to be in DRAM. And there are many ways you can say, hey, I want these places in DRAM for your data. One way to do that, use an array. The A in the bracket 10 means that I have the space for 10 items for the array, right? And then the way that works is basically those addresses will be inside DRAM next to each other, right? So if it's an integer array, and let's say the first item start at address 100, the next item will be at 104, and the next item afterward will be at 108, right? Then we talk about pointers, which store the address, right? The address basically will point to the location has the data, in this case, like the data value of 10, right? So star is the dereference operator. Basically, if I apply that operator on something, I try to use that as an address and see, okay, if I go to that address, what will I see? The ampersand is the reference. If I have the data, the ampersand operator will give me the address so I can locate that guy, right? You can also do operations on a pointer. Let's say it's a pointer of an integer. If I do a plus plus, it means that I move one slot for a. If a is an integer, I don't go to the next byte. I go to the next 4 bytes, and I read the 4-byte chunks as my data. Again, referencing the referencing, right? And we have the malloc example, which is when I call malloc. In this case, let's say I said malloc size of int, right? What I'm gonna get is the function input is number of bytes that we want. So in this case, size of int is 4 multiplied by 3, that's 12. So I basically got 12 bytes of free area that I can use for x. X basically in this case will be 100 because X store the address. If I do star X equal 2 means that I put the number 2, the value 2 inside the first slot. Then if I do star X plus 1, it means that I start from X, which is 100. I go one more spot, which is 100 plus 4, which is 104. But X, the size of integer is 4, right? So you go and store number 4 in there. And if you do store x plus 2 equals 8, then you put the number 8 in the third slot here. The type of the pointer tells me how many bytes we are going. If it's a character pointer, you go 1 byte at a time because a character is 1 byte. If I have an integer pointer, I go 4 bytes at a time because an integer is 4 bytes. So that dictates how far do I go. Right? Now, more, yes.
What type of error happens if you put like more than the amount you would have? So in the example, if we showed with the number 3,
Yeah.
It's for allocating. So we have 12 bytes. So what if we do like x plus 3? What error pops up?
So in this case, basically you're walking into someone else's data or something that you do not own, right? In this case, the error, sometimes we call this segmentation fault, which is, okay, first of all, what will happen? It will crash your program because imagine, basically think of address as like someone else's home, right? When you run a program, you say, hey, I want an empty house for my data, and they'll live there. You keep walking through those addresses, and then you go over, you walk into someone else's house. What would happen is you get killed. Wait. You basically is terminated by the OS because the OS said, hey, that looks sketchy, that's not safe, right? Why is it so bad for the system when it detects these kind of things? First of all, let's say that next house, which you did not own, is owned by some other program, and that program stores your password right now, right? So it can happen. So it means that it's safe for the OS to kill that running process because it's doing something unsafe to your computer. On assignment 3, you will likely, when you use malloc, and when we are asking you to do this thing, you will likely see a lot of segmentation faults, which is basically you're trying to refer to an address that sometimes you did not own, sometimes you forgot to malloc. That happens too, right? You forgot to call malloc. It means that my pointer points to some random location. Sometimes you assign that pointer to be null, which is it's not supposed to point to anything, but then you accidentally call star X, and the computer was like, that means nothing because that's like it's not supposed to point to anything. So checkbox as well, right? Even you can also double free. You free you malloc. Like every malloc has to be paired up with free because you make the space for your data when you're done with the program, free them so that someone else can use that space later. If you free twice, the system is like, that's also not right. You're not supposed to free someone some area that's already free, right? So when these things happen to crash your program, we call it segmentation fault. We can go into a little bit more detail when we are talking about virtual memory, and that's how basically that's a part of how the system detects that something fishy is going. Any other questions? Great question, by the way. More things to consider. First of all, you can have void data type. What does it mean? It means that I don't know the data type right now. Why can that happen? Yeah, sometimes you just know that, okay, some data will come in, right? But you don't know what's the data type yet. You can specify it later. So that's one thing that can happen. One example of that, like let's say you establish a network connection between two machines, right? And I say, hey, this machine will send some data to me. And I don't know what data is yet, depending on what function I call, right? Think of it this way. Let's say I want to go to Google and search, right? Somehow I want to search for an image. Somehow I search for a link, right? Depending on what I call. But when I write a program, the program has to handle, well, I mean, the same function, right? It's basically the same function called a different command. I expect different input coming in from the server, right? So that can happen, right? And in C, you can support this kind of behavior by saying, hey, it's a void data type. Because first of all, void means nothing. So it can be associated with the, like for example, a function return type. If I have a function that doesn't return anything, I can say void with the function name. It means that the function doesn't return anything. I can have a pointer be a void type. It's a void pointer, and I can declare it this way. It means that the variable a, which is a pointer, it points to some location. But right now, I'm not telling the computer saying, hey, it's a pointer for integer, it's a pointer for character. Because, I mean, to be honest, maybe in this case, I don't know. I can cast them later. So I can do something like this. That will cast my a pointer into an integer pointer afterward, and that's okay. I can do it at any point in my program. I can change saying, hey, a, rather than a void type, it becomes an integer pointer now. It basically means that right now I don't have any particular data type, then I can cast it later. Another example that if we have time today, we'll go through, which is what if I want to have a sorting function that I give in an array. I give in an array of any type, and I give them the comparator function. Basically, it's a function call that returns negative number if a is less than b, positive number if a is greater than b, and equal to 0 if a equals b. Right? But I don't know what's the type of a. It can be a character, it can be a string, it can be an integer. Right? But because my array A can be a character or string or integer or whatever, it can even be a struct, right? Depending on how I define my comparator. In that case, I can use a void function, not a void function, void pointer to work with array A, to work with array A. You actually, in that case, the function definition doesn't convert to void, but inside the function, you convert void into something else when you need to use it. Yeah. Right. Right. Yeah. You mean the comparator, right? You talking about quicksort function? Okay, so we'll go to that. But basically, inside the comparator function, right? It dictates that the comparator take in void star, because I don't know what type it is, but inside the function definition which you built, you take that void pointer, you convert on your own inside the function call. Say, hey, let's say it's an integer, so I'll convert to int star, and I just compare the two numbers. I'll show you on the demo actually. It does, right? Oh, so the last parameter is the function pointer. Yeah, it's actually, if you think about it that way, yes, it does take a function name, but in C, it's like function name doesn't really exist for the function call. The way we refer to the function is we use function pointer, which we will talk about soon. Basically, function pointer works this way. Your code is also in the memory, which means that I can point to the code, right? Because pointer point to everywhere in your DRAM. Your running program is also running when it's in memory, so I can point to the function. And the way I can refer to a function call, and I can pass in a function as an argument in your program, is I can use a pointer. We call this a function pointer. So let's pull up that concept a little bit how of casting. So similar to variable, you can change from integer to character from into double and float and all those things, right? Pointer works the same way. In star in parentheses means I want to cast this thing as an integer pointer. Float star means that I want to treat this as a floating point pointer. You can also do const. Const is a special symbol that you put in your program. And what it does is it say that thing next to const will not be changed. Will not be changed. Think of it as read only. For example, I can do const install a. In this case, it means that the pointer a can point to many things, right? But when we want to use a, as a pointer to integer, I cannot modify the data. And because const is linked to integer, yes.
Is const like never be a local variable, or
it can also be local. Can also be local. There is a reason why we do global const, which actually have to do with when you want to do multi-threading and basically when you want to use multiple CPU to run the program. And the reason why it's matter for global variable is this. Let's say you have function 1 and function 2, right? And let's say in the global level, what you want to do is you want to sum everything up. Let's say you have a bunch of items and you want to count, right? Count up. If that's an item, you keep counting up. And count in this case, let's say it's global. In this case, both function 1 and function 2 can update that guy. There are certain things that can happen where you count up from function 1 and function 2, but it does happen at the exact same time. And it's close enough that it only gets counted up once. Because this rest condition will go into more detail in the future semester. But basically, this can happen. You try to count up twice, you call the function call to count up twice, but because both of them happen at the exact same time, you ended up count up once. So your program is buggy. When you have const in a global variable, one thing you can do is like, hey, this guy, the data is not going to be changed. Which means that if function 1 and function 2 want to read that guy, it doesn't matter. It's going to be the same data. This count up once problem, because this rest condition is most of the time the problem comes in when you modify the data. If you have to write into the variable, if you mark them as const, it means you're not writing over that, which is safe for the most part. You can also do install const A. In this case, A, which is a pointer, I cannot change where A points to. It's already a static point at I. Point at this address for I. I can't change what A is pointing to, but I can change the value of A. So one of them means that I can point to any number, but when I point to it, I can only read from it. The second case is I can only point to one item. I can modify that item because I didn't say it's const int, but it's a const pointer. It means that A can only point to that location. I can then const install const A, which means that the pointer doesn't change. Also, I cannot change the data as well. It's like completely static. You can also do const on a function declaration. We're not going to use it for the purpose of this class. It's kind of used to annotate that's a static function. So now, here's what's more important for you guys, for actually for the purpose of assignment 2 and assignment 3. And to be honest, assignment 4. How would you debug your code? Right? How many people use like Visual Studio to run? Okay, so you use the debugger already, right? And it kind of works. So if you use a terminal, if you run like GCC like I do, like I go to the terminal here and I code things on my own, I have to debug. I can use GDB to debug my code. So let me first go to this skill. So remember we have this like swap example from last week that I have two inputs, I swap them, right? One thing I can do is I can do GCC. Oops. I think it's G flag. Okay, that's G, my bad, typo. This allows me to run the code, but I can also run it in debugging mode, which is paired up with this command gdb. I can do a gdb on the executable. Give me a second, the computer is hanging. Wait. Oh. All right, while it's installing, I'll do the demo later on how to use GDB. The key idea is it allows you to, first of all, set the breakpoint to stop. Like, let's say when you launch the application, you can say stop at line number 10. And when that happens, you can go line by line, or you can say keep going. And you can set multiple breakpoints. For example, stop at line 10, 11, 15, and 20. It allows you to print the value of different variable that you have right now. And it's actually really, really useful when you debug like what happened to your pointer. Why do you have a bug? The basic is you can do GDB with the program. To run, you type run. To set the breakpoint, you type break, followed by the breakpoint. You can do continue and you can step. I'll show you in a bit. All right, I'll show you when you do a demo. There's so many cheat sheets on the internet that you can use and refer to the basic command that you would invoke a lot of time when you were doing GDB. Okay, so now let's switch gear a little bit and follow function pointer. Yes. Oh, so actually it's WO. W stands for warning. It means that the dash wall basically means that I enable on all the warning. So if there's like some implicit warning that doesn't look harmful, usually GCC will not print that. WO basically print out the warnings. In most cases, it can be pretty useful when things that are making subtle mistakes can cause an actual bug. Pedantic means that it go with the standard syntax for writing C code. So usually those are like for the purpose of like lectures and class and the assignment setup. Usually those are like the two flags that you would enable because you see like all the warnings that it would try to like dictate that, hey, this thing might not be safe to run and give you all those warnings at a time. In a real setup, people like I don't use it usually, but it's because I get used to that and I kind of know to not making those mistakes. Yeah, great question. All right, so function pointer. As I said earlier, right, your program that you're running is in the memory, which means that if I have a pointer type, it means I can point to the memory location, means that I can point to my function call. I can point to my code, basically. I can have a pointer point to my code, which means that now, let's say I have function A and function B, right? From the same program, and you have the main function here. It means that I can have a pointer that points to this location. And because it's a pointer, I can then say, hey, I don't use it anymore, and now I want it to point here. I can make them switch from one place to another, right? These allow me to swap functions in and out based on the need for my program. Let's say right now I need function A, I will call function A. If I have to, for example, reset some configuration, but function A doesn't work anymore, I need to use function B. I can use the same function pointer, but now I assign to function B instead and call the exact same thing with the same function signature, but the behavior is now function B. All right. So the function pointer, the way you use it, let's say you have a function, this is right now it's a simple function. What it does is it takes an input, you add 10 and return. Any question about this? For now, the first function definition. All right. Again, function takes one input, return an integer, right? So the way function pointer works is, first of all, the pointer has a type. Function pointer also need to have a type, right? What's the type of this guy? Yes, return int, right? But you can't just say int star because otherwise that's just a single number. Eventually this becomes an integer, but you can basically the function pointer required a little bit more information. In this case, it says it's a function that takes one integer, return one integer. So that should be my type, right? Function that takes one int, int, and return one int. So basically, that's my type for the function. The way I would declare that is, in this case, I say int, right? This is a function pointer name. The name of my function pointer, and I have a star in front to say, hey, that's a pointer. The star in front basically will say, hey, that's a pointer. The int at the beginning say that that thing returns an integer. The int inside this bracket means that that takes an integer as an input. So this is the input type. So let's say it takes 5 inputs, 5 integer, for example. In this case, you do in the bracket int. If it takes 2 inputs, for example, I can do something like this. In the bracket int and int. It basically tells the computer that this thing will point at a function that takes 2 inputs and will produce an integer at the end. I can then assign to the address of func, which is this location. Now I have a function pointer called func_ptr. So func_ptr is my function pointer. It points to the function and it knows that it needs to take 1 input and it will return 1 integer. Okay. The way I would use it again is a pointer. So if I want to use a pointer, I first dereference. All right. The first thing I do is if I want to use it, I first dereference star func_ptr. That's my input. So in this case, it will print 10:10. Because you pass in 0 as an input, it returns 10. You might notice that this works like a function call, but I use a function pointer to invoke my function. All right, any question? All right, quick note on function pointer. First of all, you don't have to perform allocation because when you run a program, the space that you're pointing to is your program is already there in DRAM, so you don't have to malloc. You can get address. Basically, you can now also get the location of your function using this pointer. And your pointers can be an array. Basically, each item in your array is like different function call. You can do it that way too. And it operates. This is the most important part. It's just like a function. It behaves like a function, but now it points to the function rather than contain the function itself. Many C libraries which you do some demo, we do qsort as a demo. Qsort allow you to throw in an array and will sort the array for you. So you need to use a function pointer as one of the input, which will dictate how are you going to sort them. Are you going to sort by big to small, small to big, or whatever. This is also pretty useful to use as a callback function. For example, if this thing happen, run this. If this thing happen, run this. You can then kind of use it instead of if this thing happen, call this function. If this thing happen, call this function. You do this. If this thing happen, assign a function. Like if let's say you have function A and function B, right? If this thing happen, run function A. You set the function pointer to point to function A. Otherwise, you set the function pointer to point to function B, and at the end, after all this if else, you run the function. So the function pointer that you execute depends on whether it's going to the if or the else. Depending on whether you're going to the if or the else, and you would basically execute function A or function B. Yes. Yes. You mean the implementation of Q source, basically, right?
Yeah. Why isn't it?
Oh, okay. So here's what it assumes. First of all, it assumes that this will be giving me either less than one, less than zero, or greater than zero. So that compare function, regardless of how I call that, regardless of how I call it, if A is less than B, it should give me less than zero. If A equals B, it should give me zero. If it's greater than B, give me more than zero. Then it goes through your array, and for each pair inside your array, it basically calls that compare function and use the first item as the first input, the second item as the second input. And depending on whether you get negative number, 0, or positive number, you know whether A is less than B or not. Then you sort based on that compare function. All right, so let me kind of wrap this up with linked list before we do the demo, and I'll let you do the in-class exercise because we have a few more things that I would like you to do. Now, because you guys are not taking the DSOOP class or the data structure class yet, you haven't really learned so many of the data structure that you will know as a CS student. For the purpose of this class, because we go over pointer, I'll teach you one of the simple data structure that you have to know. This is called a linked list. You all worked with a list before, right? In Python. This is how we would implement a list in C. The property of a list is you can keep adding things in. It doesn't have a specific size. You can keep adding more things into the end of your list. All right. So this is one of the data structure that we can implement using pointer. The concept is pointer allow me to be able to point to the next item. So if I have the list that looks like this, right? Let's say this is my list. If I want to add one more thing, I just make sure the last item point to the new item. If I want to get rid of this guy, I can make sure this item points to here. Every time I draw an arrow sign here, that is a pointer. So the way I would build a linked list, right? I need two things. What's the data that you are actually storing? Is, let's say it's a list of integer, right? First of all, you need to store an integer. Then you also need to store where's my next item, right? Then you would declare a pointer that points to the first item here. Then every time you have to add more items, malloc. Every time you get rid of something, free. Okay. We'll play around with this concept during the demo, as well as the exercise, as well as your assignment. All right. So here's the basic. Linked list again, it looks like this, right? When I draw the last thing means that it points to null. It doesn't point to anything. That's it. That's the end of my list. Okay. In here, let's say it's a linked list. It's a list of integers. Let's say it's a list of integers. There's like number 1, 4, 2, 8. For example, it's like 1, 4, 2, 8. That's my list. Inside here, if you break it down, right? What do you need inside this node? Inside this circle? What do you have to store to maintain the list? Yeah, you need a pointer, right? You need a pointer. You first also need the integer, right? To store number 1, it basically have to have two things, a pointer and the data type you want to store itself. How do we implement that thing? What can we use? So we can use integer. We cannot use pointer. Can we use struct for this? Right. So we can use struct for this. So inside the struct, right? So let's say we let's assume we call this node, right? It store the number I want to store, right? Just give me a second. Someone call me. All right. So basically, you have a struct, right? The first thing you have to store is your data itself. You have to store an int. What's the type of the pointer I want to point to? Let's call this next. Let's call the name of the pointer next. But what's the type of this pointer? It actually doesn't point to an int. It actually points to a struct node. So the type is struct node, right? So this way I would do this is struct node pointer, right? In this case, it points to its own type. If you think about it, this point to my own type, because that's what we want. I want to make sure the pointer points to the next node, right? So that's what you have to store. Now, these are the functions that my linked list should be able to do. And you can kind of define it whatever you want, right? But here is the basic premise. First of all, if I have a pointer that looks like this, right? I should be able to, first of all, point to the first guy. Second thing is I should be able to insert, right? Let's say insert at the end. And I should be able to remove at location X. So let's say I want to remove at 0 means that I get rid of first node. If I remove at 1, I get rid of the second node. So these are the basic operations. And I mean, what else you want to have is whatever you want to design. You can say, hey, does it have this element? So like has with some input. You can maybe want to do insert at position. It means that go to this position and insert the whole thing. Insert the new node. Yes. What happens when you get to the end? Well, I mean, that's it. You know that. Okay, here's the thing. You need to know that's the end. How do you check that? Yeah. Huh? You can make, so basically the easiest thing is everything here is a pointer, right? It points to the next guy. So they just said this point to now. So you can loop around and look at the pointer. If it doesn't point to now, it means that you can keep going. That's basically one thing you can do. While, right? This thing point to now and put not in front of them. It's like, wow, this is not now. Pointer equal to pointer next means that I go to the next item, right? In a struct, right? In the struct, the way you access things inside the struct is you have the dot operator. Like for example, you can do a dot val means that I go to the val element of my struct. In this case, because a is a struct itself. If I have a struct pointer, right? I'll go back one slide here. This is a pointer. It's not the struct itself, it's a pointer to the struct. One thing you can do is you can do, let's say this is name, this node is named A, or like whatever, I just name that node A. I can do A, right? Because it's the pointer, I can do A dot next, and then the reference to get the location. The easier things to do in C is you can do this, A. This thing that looks like an arrow, like the minus sign with the greater than, that looks like an arrow, is a short form that C allow you to do. You can do A next. It knows that will go to the next item. All right. So that's how you can implement the linked list. So again, reference for the C manual for a normal manual how to write program in C, and also the standard library things that you can call from the standard library, which include malloc. Now I'll do a sample code. First of all, I'll show how to use function pointer to call the qsort function. Then I'll show you some example of linked list implementation. All right. But before we go there, let me pause the recording quickly so that we can focus on the example. All right.